Hello everyone, thanks for tuning in and thanks to the organisers for inviting me to give this talk today. So I'm going to talk about some work that I've been doing with David and Rob, which works towards unscrambling the quantum omelette. This is work that is not yet an archive. Hopefully it will be soon, but I also said that a year ago when I last gave this talk, so don't hold your breath. So what is this quantum omelette? So it comes from this quote by E.T. James over 30 years ago now, who says, "Our present quantum mechanical formalism is not purely epistemological. It is a peculiar mixture describing in part the realities of nature, in part the incomplete human information about nature, all scrambled up by Heisenberg and Bohr into an omelette that nobody has seen how to unscramble." Well, I said this was 30 years ago, and I would argue that this is still a problem that's entirely pervasive in our way of thinking about quantum mechanics today. Indeed, a lot of the work that goes on in quantum foundations has really just served to solidify this problem, from generalized probabilistic theories to ontological models to categorical quantum mechanics. They all start with this omelette and build on it. So James went on to say, "Yet we think that the unscrambling is a prerequisite for any further advance in basic physical theory. For if we cannot separate the subjective and objective parts of the formalism, we cannot know what we are talking about. It is just that simple. So we want to speculate on the proper tools to do this." So in this talk, I'm going to do just that. I'm going to speculate on the proper tools to do this. So I'd also like to mention our personal motivations for studying this problem. We came at this really as an attempt to resolve certain conceptual and technical issues in the literature involving definitions of operational theories and ontological models and of Speckman's notion of generalized contextuality. And in trying to resolve these various issues, we kept sort of running into this omelette-y mess. And so the subsequent unscrambling of the omelette that we've done has all been in service of trying to gain a deeper understanding of contextuality. And hopefully that will become clear later in the talk. So the aim of this talk is to speculate on the proper tools for unscrambling the quantum omelette. I'm going to build these tools on two primitive tools. First of which all of you should be familiar with are process theories. So here we have processes, U, V and W, connected together by systems. But more than that, we're also going to talk about maps between process theories, these diagram preserving maps, which I will denote by these shaded boxes. And the diagram preservation condition is very simple using this notation. It simply says that if we first map all of our processes into the new process theory and compose them, it's the same as composing them and then mapping them to the new process theory. So the overview for the rest of the talk is as follows. I'm going to present a framework which unscrambles the omelette into two different parts, and then I'll apply this framework to get a deeper understanding of operational theories, ontological theories, and of ontological models. And then we'll see how to re-scramble everything to regain some of the more traditional notions that we're used to. In particular, this will involve defining a notion of inferential equivalence of processes, and ultimately this will give us new insight into Speckman's notion of generalized contextuality. And then I'll conclude by posing some open questions and some future research directions that I would like to pursue. So to introduce this framework to you, the framework is known as the Causal-Inferential Framework. The reason for this is that it's got two components. It's got a causal component, which represents what James called the realities of nature, and it's got an inferential component, which James would call the incomplete human information about nature. And the causal-inferential framework tells you that when you generate a causal inferential theory, how these two components should interact with one another. So firstly, the causal component. This is described by a process theory, and hopefully the examples later will clarify exactly how you should think about this. But fundamentally, it represents a hypothesis about the causal mediaries that you're interested in and the mechanisms that transform between these. So these diagrams should be read bottom to top, and we have the systems of the causal mediaries, the processes, the causal mechanisms, and note that some of these mediaries will be deemed to be classical. So when I say that these are the fundamental causal mediaries, this is where we see a divergence between our formalism and previous formalisms. In particular, if you consider the example where you've got a Bell experiment and you believe that there is genuinely a superluminal influence between the two wings, then the manifest experimental structure will look something like this. And this is usually the sort of diagrammatic structure that would be used in a GPT representation, say, of a Bell experiment. In contrast, to use our formalism, if you believe that there is a superluminal influence between the two wings, then you've got to draw it. This is what our formalism says, that if there's a mediary, if there's a causal mediary, you draw it on your diagrams. So I've been a bit vague with defining what this causal process theory is. And the reason for this is because you'll choose different sorts of theories, different sorts of causal process theories to do different things with this framework. So for instance, you'll make one choice for what the causal process theory should be like if you want to talk about operational theories, as we will later, and you make another choice if you want to talk about, say, ontological theories, as we also will do later. Now let's move on to the inferential process theory. We can be quite a lot more concrete here about what this is, because it doesn't vary so much when we want to consider different situations. So the first part of this is describing Bayesian probability theory. And here we have the systems drawn going from left to right to distinguish them from the causal systems that go from bottom to top. The systems in this case are just finite sets, and then the processes are stochastic maps. So for instance, the states here are just probability distributions, and the effect is unique and describes marginalization. The second part is Boolean propositional logic. So again, we're going to take the systems just to be sets, and we describe propositions as being yes-no questions, which can be thought of as functions from some set X to the answer set B, which is yes-no valued. This means that we can describe logical operations between propositions with a nice graphical representation. So here we see how to encode the logical OR of two propositions by first copying the variable, asking questions about the two copies, and then taking the OR of the answers. So this gives us a useful graphical calculus for reasoning and doing propositional logic. In particular, this allows us to see that some generic function from, say, y to x can be thought of as a Boolean algebra homomorphism from the Boolean algebra over x to the Boolean algebra over y, defined as so. So, for example, we can easily see that it preserves the logical OR, and this really just boils down to the fact that a function is copied by the copy dot. However, it's not always useful to think about propositions as being questions. Sometimes we prefer to think of them as effects. To do so, though, we have to go beyond talking about functions between sets and instead talk about partial functions between sets. So, for example, we can encode a proposition about x as being a partial function from x to star, where star is the trivial object singleton set. And this means that we then can encode the truth values for propositional logic as being scalars. So we now have two scalars, true and false, where formally true can be thought of as the identity function from the singleton set to itself, and false is the partial function with the empty set as the domain. Then finally we can talk about value assignments, which are the states in Boole, and they assign, for example, can be thought of as assigning the value little x to the variable x, but more than that they also assign the answer to the propositional questions, and they also assign a truth value to propositional effects. So with these two parts in play, Bayes and Boole, we put them together to give our full theory of inference. So the way to do this is to first note that they both can be viewed as sub-process theories of process theory substock, in which systems are finite sets and processes are substochastic maps. And then we can realize that any substochastic map can be achieved through composing elements of these two primitive process theories through a diagram such as this one here, where S and W are elements of Bayes, they're stochastic maps, and this Y is a propositional effect from Boole. So this means that our theory of inference really is just substock. It's very simple. But while this endpoint that we've got to is very simple, I think the way that we've got there by understanding the interaction between Bayesian probability theory and propositional logic is very interesting. And also I think that the graphical calculus that we've got here for talking about Boolean propositional logic has a lot of potential to be very useful. If anyone knows of any place where this has been done in the literature, I would be very interested to hear from them. So let's now put together these basic elements to define a causal inferential theory. Schematically, a causal inferential theory looks like this. We have the causal process theory cause and the inferential process theory inf, and these are combined together via two diagram preserving maps into a process theory we call CI. And then we're going to make predictions by using another map that takes us back to inf. So now let's talk about what CI is. So CI includes all of the systems from the causal process theory and the inferential process theory. And it also directly includes all of the processes from inf. And so in some sense, it's really just an extension of our theory of inference. We will denote this inclusion of the process from inf via this diagram preserving map, I. So this equation here maps S in inf to S as a process in CI. We will then define three generators and a bunch of rewrite rules to define how this inferential subtheory interacts with the causal systems. And that will define the full process theory CI. So the first interaction describes what we know about a causal mechanism. So for every pair of causal mediaries, we'll denote the set of causal mechanisms transforming one into the other by this symbol, A arrow B. And then for each pair of causal mediaries, we'll have an interaction that lets us specify what we know about the causal mechanism. So in particular, this diagram here tells us that we have state of knowledge sigma about how causal mediary A transforms into causal mediary B. This has a bunch of sort of obvious consistency conditions. I won't talk about all of them in detail, but let's look at this one. This says that suppose we have some state of knowledge about how A transforms into B, and then we have another state of knowledge about how B transforms into C. Then we should be able to combine these two states of knowledge via this stochastic map to tell us what we believe about how A transforms into C. So to define this stochastic map, let's look at its action on point distributions. So say that we know for sure that the transformation from A to B is little t, and then we know that the transformation from B to C is t prime. Then what do we know about the transformation from A to C? Well, it's just that first t happens and then t prime happens, where this composition is the composition within the causal process theory. So we're encoding the structure of causal process theory in this set of stochastic maps. So similarly, we encode the probabilistic structure, the parallel composition structure as well in a very analogous way. And also we encode the identities and the swaps too. So for instance, if we know for sure that the identity transformation happened, then we just represent that as the identity in CI. And similarly, if we know for sure that the swap happened, then we represent that by the swap in CI. The second interaction tells us what we learn from a classical system X. So for each classical system X, we have one of these interactions, which lets us learn the state of the classical system. And having learned the state of the classical system, then we can ask propositional questions about it. So here we learn the state of the system X, and then we ask propositional question pi and get some answer in system B. This again will satisfy some consistency conditions. For sequential composition of these, if we learn the same thing twice, it's the same thing as learning it once and then copying what we've learnt. And we have, again, similar thing for parallel composition. And finally, if we learn something and then throw away or marginalize or ignore what we've learnt, it's the same as doing nothing. So the final interaction describes what we want to ignore. So we want to be able to ignore causal systems. And we view this as an interaction because we view this ignoring process as being an inferential sort of process as opposed to being a causal mechanism. This shouldn't be thought of as physically putting a system in the bin. It's really just my choosing to not pay attention to something. So this must satisfy the obvious composition analogy constraint, namely that if I ignore a pair of systems, it's the same as ignoring the composite system. So finally, to define the process theory CI, we have a consistency condition between the first and the third interactions, which looks like the following. So this means that if we have some state of knowledge about how the causal mechanism behind which A transforms into B, but then we just ignore the system B, then this means that what we think about the transformation is totally irrelevant, and we may as well just be ignoring the input causal mediary A. So that sets up this process theory CI, but I said that also we want to have this embedding map E, which lets us represent our causal theory in CI, and also we need to be able to talk about predictions, this prediction map P, so let's introduce those next. So firstly, we have this diagram serving map from the causal process theory into CI, and this is defined on processes in cause as follows. We map the process T to the state of knowledge about the transformation from A to B, which is the delta function state of knowledge that T occurred. And to see that this is diagram preserving is very simple once we have those rewrite rules for this generator here. So in particular, we can start with the two transformations in sequence, we can compose them within cause, and then we represent that as the delta function state of knowledge about how A transforms into C. But then we know from the definition of the stochastic map that we can break this up in this way, so that first we have a state of knowledge about how A transforms to B, and then how B transforms to C. And using the rewrite rule for our generator, we can split that up into a state of knowledge about how A transforms into B, and then how B transforms into C. And then by the above definition, that's just the action of this map E twice. So we've got at least sequential diagram preservation, and it's easy to generalize that. Finally, the predictions. This should only be a partial diagram preserving map, or a diagram preserving partial map, and it's from CI through to inf. So it's only a partial map because we only expect to be able to make inferences when we don't have any causal mediaries floating around disconnected. So we have this diagram D, which has only inferential inputs and outputs. It could have causal systems somewhere in the middle of it, some arbitrarily complicated structure, but we expect to make a prediction about the situation. We can think of this as how to make inferences about the output given the input, say. Whereas if we've got causal mediaries that are disconnected, then we don't expect to be able to make predictions, so this is just undefined. The predictions that we might want to make could depend on the causal path, for instance. And there's a consistency condition for this prediction map, which says that if we have some process in CI which came directly from inf in the first place, that when we map it back to inf using P, we get back to where we started. We also find a constraint on the predictions that come from this interaction between our two generators. So take this example. We have some scenario where we have some state of knowledge sigma about how some state is prepared. We have proposition pi about that system. And then we have some state of knowledge tau about how it's going to evolve. Then this should give us a probability in inf. The probability that pi is true given states of knowledge tau and sigma. But this rewrite rule means that ultimately we can just ignore the state of knowledge tau. So the probability that pi is true depends only on the state of knowledge sigma. So what we know about the causal future for some proposition is irrelevant. This means that the valid inferences that we can make are constrained by the causal structure. They don't dictate it. And this is in contrast to many other approaches where you start with, say, some no signaling conditions and try and drive the causal structure, which is to constrain the causal structure by the inferences that one can make. So that is the Causal-Inferential Framework in a nutshell. So to briefly recap, we have this structure for a causal inferential theory. We have the causal component and the inferential component. which are then brought together via two diagram-preserving maps, E and I, into the process theory CI, where they interact with one another. And CI can be thought of as really like an elaborate description of the sort of causal inferential setup. But to then actually be able to use this framework to make any predictions, we have to map ourselves back to inf to get some inference or some prediction about one of these elaborate setups. So the claim is that this really achieves our goal. It's provided a framework which has unscrambled the omelette. That is, we have the causal process theory representing the realities of nature, and we have the inferential process theory describing the incomplete human information about nature, and we clearly see how these two interact with one another to give rise to the full causal inferential theory. So having now set up the causal inferential framework, let's look at some applications of it. The first application that we have in mind is to define what an operational theory is from this perspective. That is, it's a causal inferential theory of procedures. So we refine this sort of vaguely defined process theory cause into a much more concretely defined process theory Proc. So what is Proc? Well, Proc is a process theory in which the processes are viewed as being lab procedures, or maybe more specifically as being lists of instructions about what you should do in a lab. And then the systems represent the complete set of hypothesized causal mediators. And remember that these don't need to be manifest, they don't need to be things that you can sort of point at in a lab, they can be hidden ghostly influences as well, if you believe in them, that is. To be a bit more specific, it's useful to realize that Proc is what we call a free process theory. That is, there's no non-trivial equalities within process theories, just those that you get by sort of sliding things around on the page that every process theory must satisfy. So for instance, when we compose two lab procedures in sequence, this is thought of as really just like a concatenation of the lists of instructions corresponding to each of them. So there's no sort of reduction in this at all. It's just T and then T prime. Similarly, for composing things in parallel, this just again corresponds to both of those lists of lab instructions. It doesn't simplify in any sense. So this is so really then a diagram is just a complete description of the experiment where each process is specified by the list of lab instructions, and then where all of the causal mediators are specified. Some particular scalars in Proc then are just going to be some complete description of an experiment in which we don't think there's any relevant causal inputs or causal outputs to the experiment. It most definitely is not equal to some probability. So normally, I think when you see a diagram like this, in quantum physics at least, you are very tempted to interpret it as a probability. That is definitely wrong here. Here scalars have a huge amount of structure to them. So then you might want to know, okay, how do I get a probability out of Proc? Well, it's a two-step process. The first step is that you map yourself through to the process theory PI, where it can interact with the inferential component. So this is, we embed these as delta function states of knowledge in that process theory, and then we apply the prediction map to take us to inf. And then we'll get some probability associated with this diagram. This probability, however, will, in this case, always be equal to 1. And the reason for that is that to get some probability other than 1 in the procedural inferential theory, you have to include some non-trivial proposition at some point. And you don't get any propositions coming out of this embedding map, so the only probability we can get is 1. Now, the second thing we want to talk about are ontological theories. So within our framework, these are causal inferential theories of functional dynamics. That is, we replace this generic causal process theory with the process theory Func. So what's that? Well, the systems are now all labelled by finite sets, but these have an interpretation as representing ontic state spaces. So the elements of these ontic state spaces are known as ontic states, and they represent a definite state of reality for the system, and they completely specify all of the properties of interest for that system. So these we then stipulate evolve in time under the application of functions. So the dynamics, the possible dynamics for these state spaces are functional dynamics. This is in contrast to other approaches to ontological theories, where often the dynamics have been given by stochastic processes. But here we view the stochasticity that's been associated to earlier works as being part of the inferential theory. It's due to our ignorance about the underlying functional dynamics that the systems undergo. So let's consider the scalars here. Well, we find that there's just a single scalar, which is the unique function from the singleton set to itself. And so in contrast to Proc, we find that Func has many non-trivial equalities. It's got a very rich structure. Moreover, we also add a bit of extra structure, some extra conditions to the process theory Fi by saying that every system is viewed as being classical. That is, we have one of these generators that lets us learn something about a system, but now for arbitrary systems. We also have an extra rewrite rule, which is this one here, which is very useful, which says that whatever we learn about the output system, lambda prime, we can instead learn about by processing what we know about the transformation, about the function, and what we know about the input system. So this black dot we have to define, and it's defined as follows. Suppose that we know that the input state is lambda, little lambda, and we know that the functional dynamics transforming it are given by the function f. Then we know that the output state is going to be given by f applied to lambda. Now, as I said, this is a very useful rule because it lets us come up with a very simple normal form for the diagrams in Fi. In particular, it looks like this. So we just have the two generators, two basic generators, and then some substochastic map coming from inf, wired together in this particular way. That's not important at this moment. What is important, though, is that this means that we can prove that there's a unique prediction map for this ontological theory. It's very simple to prove this. First, we just note that any diagram D can be rewritten into normal form as follows, and then apply the prediction map to both sides, and then use the consistency condition for predictions. And so we see that the prediction associated to this map D is just this substochastic map S. Now, with the definition of an operational theory in place and the definition of an ontological theory in place, we can very, very quickly define what an ontological model of the operational theory is. Very simply, it's a diagram-preserving map, Z, mapping Pi into Fi, which satisfies two constraints. Firstly, it preserves predictions. So if we make some prediction in Pi, taking us to inf, well, that's the same as first mapping us to Fi and then making a prediction in the ontological theory to take us to inf. Note these two copies of inf are the same, and this is a long equal sign here. So that's the first constraint, is that predictions must be the same in the original theory as in the representation. And secondly, ignoring a system has to be represented by ignoring a system. So if we ignore a causal system in the procedural theory, that's the same as ignoring a causal system in the functional theory. So I think the only controversial part of this definition, I hope anyway, is this assumption that this map should be diagram preserving. This is a very useful condition to demand, and it has many consequences to it. But fundamentally, I think within the setup of our formalism at least, it's really quite unarguable. As we said, the diagram in the procedural inferential theory isn't sort of the manifest experimental structure that you can see in the lab. It's representing your best hypothesis about the fundamental causal structure. That is, it includes any influences that you would believe should be there. And so then if you want an ontological model of this, well, the ontological model is supposed to be describing the sort of underlying reality. And so the causal structure in the underlying reality has to have the same hypothesis about what it is as your best hypothesis for the procedural theory as well. So there really only is one causal structure of relevance, And so this mapping from the operational to the ontological theory has to preserve that structure. We've now introduced the framework and seen how we can define refined notions of operational theories and ontological theories and ontological models within this formalism. But how do we get from this framework back to more traditional notions that we're familiar with, the omelettes that we are used to? Well, we're going to do this by introducing the scrambling procedure. And to do this, we first need to talk about what inferential equivalence is. So two processes or two diagrams in CI are said to be inferentially equivalent if and only if they look the same from the perspective of inf. So firstly, before defining this formally, what do I mean by from the perspective of inf? Well, I mean that if you have two diagrams, D and E, then every way that I can map those to inf, they should be equal to one another within inf. So how do we get from some diagram D to inf in the first place? Well, for some diagrams, namely those with only inferential inputs and outputs, we can map them directly to inf using the prediction map. But for those that have causal inputs and causal outputs, we can't do it in such a straightforward way. Instead, we first have to close off the diagram D with some other diagram T, so that it only has inferential inputs and outputs, and at that point we can apply the prediction map to take us to inf. But obviously there's many different ways you can do this. There's lots of different T's that we could use in this diagram. So the perspective on the diagram from inf really is the collection of such ways to get to inf. So we can now formally make the definition of what it means for two processes to be inferentially equivalent, namely that D is inferentially equivalent to E if for all ways that we can close off these diagrams using some process T, when we map them to the inferential theory using the prediction map, they will be equal to one another. Now the nice thing about this definition is that you can show that this equivalence relation we've defined is preserved by composition. And so we can get a new process theory by quotienting by this relation. So that's what we do. We start with our causal inferential theory and we quotient it with respect to inferential equivalence to get this quotiented theory Ci tilde. Now, these quotiented theories are the omelettes. In particular, quotiented procedural inferential theory is very closely related to the notion of a GPT, and the quotiented functional inferential theory is very closely related to the traditional ontological model framework. The details of this are subtle, so we'll not go into them now. So I've said that this quotiented functional inferential theory is one of these omelettes, and I said that it's basically the old notion of a operational theory, or sorry, an ontological theory. So I think this needs a bit of justification, as ontological theories, I think previously were always considered to be something where we really knew precisely what was going on, and it's where people would have said that we already had a clear separation between inference and causation. So I'm going to try and persuade you that that's not the case through a particular example. So consider the four possible functions for the set 0, 1. We've got the identity function, we've got the not function, we've got the prepare 0 function, and we've got the prepare 1 function. Now, the first two of these, I think we'd all agree there's definitely a causal influence from the input to the output. Whilst in the second two, these are represented by discarding and then re-preparing something. So in the second two, there's definitely not a causal influence from the input to the output. I hope everyone would agree with me there. So now let's consider two particular states of knowledge. The first, sigma con for connected, is half the identity plus half the not transformation. And so this is a probabilistic mixture of situations where we are certain there's a causal influence from the past to the future. And then we've got sigma sep, which is a probabilistic mixture of prepare 0, prepare 1, and here is a probabilistic mixture of cases where we are certain there is not a causal influence from the past to the future. But let's now say that these are states of knowledge about a transformation that's actually happening in the world. Should these be equal to one another? Well, in the functional inferential theory, these are definitely not equal to one another. They paint very different pictures of the ontology of the world. In one case, they paint a picture where we are certain there's a causal influence, and in the other case, they paint a picture where we are certain there is not a causal influence. We might not know exactly how the causal influence is, but we know that there is one. But these things, you can quite easily show, are inferentially equivalent to one another. And so in the scrambled theory, in the quotiented theory, these are equal to one another. So in the old notions of ontological theories, you wouldn't be able to distinguish between these two situations, even though on an ontological level they are most definitely different to one another. So what this shows us is that the quotiented theories cannot generically distinguish between situations which have causal influence and those which don't. And also they can make the opposite mistake. There can be an inferential influence which is mistaken for a causal influence. So what this means is that states of knowledge about functions are not the same as the stochastic maps that you would associate to them. They're different things. And so this in particular means that our new notion of ontological models are not the same as the old notion of ontological models. So the old notion would have been that you have a map from Proc to the quotiented functional inferential theory of stochastic maps, whereas our new notion is a map from the procedural inferential theory to the functional inferential theory. And so these are quite radically different perspectives on the matter. And so we're talking about ontological models, so the natural thing to ask about is contextuality. In particular, the notion of generalized contextuality put forward by Speckens. So within our formalism, it looks like the following, commuting square. It's that some ontological model mapping from the procedural inferential to the functional inferential theory is said to be non-contextual if and only if there exists some diagram-preserving map from the quotiented procedural inferential theory to the quotiented functional inferential theory, such as I said, this diagram commutes. So this means that the equivalence class of transformations in the procedural inferential theory all get mapped to the same equivalence class of functions in the functional inferential theory. So to put this into words, the old notion of generalized contextuality was that things that were operationally indiscernible were ontologically identical. That is, that if we couldn't do any experiment to distinguish two things, then they should be represented by the same thing ontologically. Our new notion is, I think, more refined than this and more correct than this, and it says that operationally inferentially equivalent things are represented by ontologically inferentially equivalent things. So this is, I think, quite a radical change in perspective on what contextuality fundamentally is about. Okay, so to wrap this up, this has been a brief run through quite a elaborate and extensive research program, but I've tried to at least give a flavour of what the Causal-Inferential Framework is about and the ideas behind it. I've tried to give some concrete examples of how this can be applied to operational theories and ontological theories and models of operational theories as an ontological theory. We've seen how we can recover more traditional notions of generalized probabilistic theories and the older notion of an ontological model via this re-scrambling, this quotienting by inferential equivalences. And in doing so, we've ended up with a refined notion of generalized contextuality. So there's a lot of open questions. This is work that is said it's not published yet, so it's still in the early stages. So I think the main open question is, what about quantum theory? we claim that this formalism has unscrambled the omelettes of operational theories and of ontological theories. But what about quantum theory, which was our starting point? So to my mind, what we want is something that's like the functional inferential theory, but where it describes quantum theory as opposed to classical theory. So I think to actually get there, we need one of two things. We are either going to need to update the inferential side of things and come up with some intrinsically quantum theory of inference, or we're going to have to modify the sort of ontological side and come up with a sort of quantum ontology that behaves as the causal theory. Maybe more likely is that we'll have to do both of these in order to get some sort of satisfactory resolution to these deep problems in quantum theory. There are many other open questions as well that we can try and address at this point. The first couple really are about further refining this formalism. I think it would be great to have a fully categorical formulation of this to try and more cleanly define things, and also to try and understand what these diagrams we're drawing that have sort of two directions to them actually correspond to. Hopefully having such a formulation will also let us go beyond all of these assumptions that we keep making, that the sets like the ontic state spaces, for instance, are finite. I don't think there's any technical reason why this can't be done. It's mainly that we just don't have the technical expertise to push all of it through at this point. In terms of future directions and applications of this formalism, I think it'd be interesting to come up with a reconstruction of quantum theory from this perspective. A lot of things that you have to do a lot of work for in reconstructions seem to basically be coming for free. A lot of the convex structure and that kind of thing. Also, there's interesting connections to be drawn, in particular between the ontological theories that we've defined and classical causal models. We've got some very preliminary stuff here, but I think there's much more to be explored here. Can we come up with sort of a framework for causal inference using these ideas to try and replace Pearl's formalism, for instance? I mean, there's many other open questions that we want to explore, and I hope this is a framework that other people are interested in, and if you've got any ideas about how you think this could be used, please get in contact. Anyway, thanks everyone for listening, and I'm very happy to answer any questions that you might have. Thanks.